Hello, and welcome to my screencast. My third year project is an augmented reality car, part of a programming teaching tool. The aim of the project was to create an alternative tool to robotics in teaching programming within schools. The solutions aim to be more accessible and cheaper than the alternative systems, yet have similar properties, in that the car needs to be able to accept a series of commands to solve some form of problem. There are three components that are necessary for augmented reality. The first is a camera, the second is a set of features or marker to represent the place the car should appear, and the third is a screen to visualize the augmented scene. The goal of the teaching tool is for the user to move the car from the center of the marker to a finish point within a set workspace, using a series of commands such as forward, back, left and right, with parameters being the number of units to move. The idea is that the movements are functions, with the units being function parameters, and the overall created set of movements is the program. The application has three main windows, the first being the window that contains the augmented scene. The second is a command window which contains all the commands the user enters. The third is a help window to give the user some assistance with any queries they may have. The marker can be placed within the workspace and the car appears on top of it. The marker can be moved and the car will follow. The augmented reality was created using a computer vision library called AR Toolkit and a graphics library called OpenGL. The following pipeline describes the stages in generating the augmented reality scene. After obtaining a video frame from the camera, the program needs to find the marker within the frame. When the marker has been found, the pose of the marker needs to be calculated and is represented with the matrix T. The marker needs to be recognized so the center pattern is compared using template matching. Once verified, the matrix T can then be loaded into the graphical camera so that any object that appears in the graphical scene is located at a position above the marker. Once the user is ready, the workspace can be set on by right-clicking in the main window. A map will be generated showing the workspace limitations and positions of the car and finish point. The red in the map represents the classified workspace, the blue represents the car position and the yellow represents the finish point. The finish point now appears within the augmented scene, along with some other information about scores and movement size. The user can add commands and each is run every second. When the user runs a set of commands like the one in this example, the map is updated and checked for accessibility. If an object or an edge is reached, the commands stop and the user needs to remove the commands and carry on with something else. Here is another example of a puzzle with some inputted commands. Once the car reaches the finish point, the puzzle is complete and a new one is generated for the user to solve. The real-world detection is carried out with an area of computer vision called image segmentation. The aim of the segmentation in my application is to split the areas of image into two sections, accessible and inaccessible. To do this, I use an algorithm called seeded region growing across multiple stages. The first stage segments the white area surrounding the marker, and the second stage segments the area surrounding the white. The segmentation algorithm works by obtaining models of pixel color values in various locations surrounding the marker, and then moving throughout the image in all 8 directions, obtaining samples. The samples are set to accessible and compared with the model. If similar enough, the algorithm continues on throughout the workspace in the similar sample directions. A total of 4 segmentations with 4 models are each calculated for the first stage, and a total of 8 segmentations with 8 models for the second stage. By doing this, the algorithm is more robust and is more likely to segment the workspace correctly. The following illustrates the equations used to complete the similarity. A covariance matrix was calculated for the model, inverted, then multiply with the differences between the means of the model and the sample. The result gives a square standard deviation. If this value is less than or equal to 9, then the sample and model are similar enough. When forming the model and calculating the covariance matrix, I use the hue and saturation values from the HSV colour space. By doing this, the value of brightness won't have an effect on determining the similarity, and so the solution will be more robust to different lighting across the workspace. To check the car movement's validity, the graphical position needs to be converted into the image/map coordinates. A matrix M is therefore needed to multiply the graphical position to get the map position. To calculate this matrix, I use a least square method by mapping 4 points between the graphical and image coordinate systems. These 4 image and 4 graphical points were set to the marker's corners and were entered into the equation 1. The 4 graphical points are xn, yn, and image points are x'(n), y'(n). The equation 1 can then be rearranged to get all the elements of matrix M, following the steps of equation 2. The values in M can then follow the calculation in equation 3 to go from graphical to map. The calculated points can then be indexed into the map, where a value can be obtained to check if the position is safe to move into. The various puzzles that the user has to solve are randomly generated. The puzzle generation algorithm works by first choosing a set of random directions from up left, up right, down left, and down right. It then, for a random number of iterations, chooses one of those directions randomly for each iteration up until it reaches the boundary. The teaching tool has other features such as a distance indicator to show how far the car will move with the current movement size, changing of the car size, and movement using keyboard controls. The final application meets all the requirements that were set at the start of the project plus more. The tool is fun and easy to use, and with some UI improvements could be integrated into the UK computer science curriculum, which would hopefully inspire children to become more involved in computer science. Thank you for watching my screencast.